to rotate itself. So you can, in this point, you can go from this orientation, so you can go to this orientation, or at this point you can go to this orientation. You can go to any orientation you want. So the wrist will give you the ability to do that. Okay? By just rotating the wrist, you can keep these links fixed. You just rotate the wrist and you can generate any motion or any orientation you want. So basically, we'll have three parts, right? We'll have the manipulator structure, links, joints, a wrist, and an end effector. Okay? All right. So to study the motion of all the three, when we develop a mathematical model, we need to relate the motion of each of the frames or each of the links to this. Okay. If I move theta 3, let's say I change theta 3, the end effector will move, right? So if I change this, it can go up or down. Does it affect the previous links? No. But if I do change this, all the consecutive links are going to be displaced, right? Because if I move this, the whole chain is going to move. So we need to associate a frame for every joint. So first frame that we have is a global reference frame. X0, Y0, and Z0. Okay? This is a global reference frame. This is where you have the base of the manipulator. So we call it O0. Origin is O0. This is our global reference frame. Or global frame of reference. Okay. Some books, if you're following a different book, you might call it a world reference frame. Or a fixed reference frame. Depends on what you want to do. They all mean the same, global, world, or fixed. Because this is fixed, it does not move. Okay? So this is a fixed frame of reference. Then we have the manipulator. Let's consider a very simple. So every joint, what we'll do is we'll associate a reference frame here. So this will be okay. So this will be 0. O1, X1, Y1, Z1, O2, X2, Y2, Z2. Here we'll have Y3. And the last one is, we'll call it as YE, XE, which is the end effector, and ZE. This is O. Okay. So O1, O2, O3. These are joint frames of reference. Okay. OE is your end effector frame of reference. So when I generate any motion about this, the origins of all other frames will move. Okay? If I change O3, only OE will be affected. If I change O1, or from here, any motion from O0, all these frames will move up or down depending upon the relative motion between them. So these joint displacements, let's say we have, let's say this is a 3 degree of freedom manipulator, 3 DOF. The instantaneous position of the manipulator is defined by the angles here. This is theta 1, this here is theta 2, let's say this is theta 3, okay, and this is theta 4, but let's ignore the wrist for 1 second, let's forget the wrist for a second, let's only focus on the legs. We'll talk about the wrist leg. So Q is known as theta 1, theta 2, this is known as the joint vector. Okay, it will define in what position the manipulator is currently in. So if theta 1 changes, this vector will change and so on. So the instantaneous position of the manipulator, this will define the current, posture of the manipulator. If you know thetas, if you know all the thetas, then you should be able to calculate the position. So let's say this is the position P of the end effector. So P is nothing but a function of P, right? If I know all the joints, then I should be able to tell what is the position of my end effector. So this is a function of theta 1, theta 2, okay. So if I give you the joint angles, you should be able to tell me where my manipulator is currently positioned in space. So P, as you know, if I give you the wrist angles, you should also be able to tell me what is the orientation. This will be X, Y, Z, phi, theta, psi. Okay. So this relationship where you know, knowing the joint angles, you can calculate the position is called forward kinematics. Okay. Forward kinematics is to calculate the position and orientation of the end effector given the joint displacements. Okay. Given the joint displacements, if I give you what the joint displacements are, you should be able to tell me what is the position of the end effector. Sometimes we call it P, sometimes we use the letter X, a capital X. Now, what happens if one of these links, instead of being revolute, I change them to being prismatic? If I change, let's say if I change this joint to being a prismatic joint, which is a joint like this, okay, then instead of theta 2, I'll have D2, because D is representing linear displacement. So Q will change here to theta 1, D2. Okay. If one of the joints instead of revolute becomes a prismatic joint, then you'll change theta to D. Okay. D reflects your linear motion, theta reflects your angular motion. Okay. So when I say a joint displacement, it is understood that if it's a revolute joint, it's a angular displacement. If it's a prismatic joint, it's a linear displacement. Okay. So we're not going to argue about it, why am I writing theta or D. It is assumed that if this joint is D, then this will become D2 and so on. Okay. The inverse problem, what is the inverse problem of this? What is the inverse problem of this? What is the inverse of forward kinematics? The inverse problem is, I want to get to this point. What should be my joint displacements? Which is a very realistic problem. You have a robot fixed, you have a workpiece here, you want to inspect the workpiece or you want to get into a particular orientation to pick it up, and you should know how to displace these angles, what joint displacements should be created to get to that point, because otherwise you won't be able to operate it properly. So the inverse kinematics is basically the kinematics problem is this. Find Q knowing what is P, right? You want to find the joint angles once you know the position and orientation of the end effector, right? F inverse, or you could call it G, you can call it another function. Okay, so this is nothing but find the required joint displacements to generate or to reach a given point with a given orientation. Okay. So in other words, you're trying to find Q. Find Q given P. Okay. Find Q given P. In this case, you find P given Q. Okay. This is the opposite, inverse kinematics and forward kinematics.
Doctor, again, what's the purpose of inverse?
Okay, so I'll tell you, let's say that I have a manipulator here, right? I want to reach this, I want to pick it up like this, okay, or I want to pick it up like this. What should be my joint displacements? How can I reach this point with this orientation, right? This has to be known to you so as to be able to generate different kinds of motion, okay? Now, the problem is this, since we are talking about inverse kinematics, just to give you a heads up. Okay. Let's talk about this. If I give you a set of joint angles, let's take a very simple manipulator here. Let me draw it. A very simple one. It's like your arm. You can tell me very clearly. Just imagine this and you can give me an answer very easily. Let's say that I have a 2 degrees of freedom like this. Okay, and this is my end effector. I want to reach, this is in a 2D plane. It's not too complicated. Theta 2, theta 1. Okay. For a set of joint angles, so let's talk about forward kinematics. Forward kinematics, right? If I give you theta 1, theta 2, will P be unique or P will be, you can have multiple P's? What I mean is, for a given set of joint angles, can you have more than one P?
Yes.
Yes? How?
We move upward and downward, so there's a transition.
If you move upward and down, to theta 1 and theta 2 is changing. I'm telling you, if I give you a set of theta 1 and theta 2, will there be more than one P?
No.
No, it's fixed, right? For this, for any given theta 1, theta 2, the point is fixed. That means this is a unique matching. This is a one-to-one matching. That means for every Q, there will be only one P. Okay? For every Q, there will be only one P. But let's take the inverse problem. If I give you inverse kinematics is like this. If I give you P, let's say I want to reach this point, will theta 1, theta 2 be unique?
No. Yeah. No.
How many of you say yes?
Unique.
Just one? How many of you think no? Why?
Because we can reach there by different angles.
You can have two different postures, right? So for example, I want to reach, let's say, this point in space, so I can reach it like this, or I can reach it like this, or I can reach it like this, right? So you can have the same point reached like this. Okay? Only for cases where the point is at the periphery of the workspace, there will be one solution, which is, in which case, this will be a straight line like this. Okay, it cannot extend. There cannot be two solutions like this or like this. It's called elbow up and elbow down configuration. So this inverse problem is a very complicated problem. Only few structures you can generate a straightforward solution, an analytical solution, but sometimes you get into positions for complicated manipulators, high degree of freedom manipulators, where you can have multiple or infinite solutions. Okay, this is a one-to-one unique matching. Here, you can have multiple inverse, multiple. It can go from no solution to one solution. Sometimes it can have multiple solutions. And sometimes it will have infinite solutions. It depends upon the point, location of the point, and the degree of freedom of the manipulator. Okay, so this is a more complex problem. This is a very straightforward problem. Forward kinematics is very simple to do, and inverse kinematics is a problem that is a complete function of the number of degrees of freedom, the types of joints used, and so on. Okay, so basically, here you have two solutions for every point. Okay, obviously, except the boundary of the workspace. Is that clear? Why inverse solution is a little more complicated as opposed to a forward kinematics problem? Forward kinematics, it's a one-to-one. If I give you theta 1, theta 2, there is only a unique position. But if I give you B, there can be multiple Qs that will get to that position. Okay. Since we are talking about the position, let's talk about let's define the workspace of a manipulator. Okay, or manipulator workspace. What do we mean by workspace? What is the definition of a workspace? What could probably mean the workspace of a manipulator?
Maybe the plane.
Huh?
Plane.
Yeah, what defines the plane? There's always a plane, no matter how you look at it. You'll always have a plane along this axis, that axis.
The base of the area that they can reach.
Exactly. So it is nothing but a set of all the points that can be reached by the manipulator. Workspace is the set of all points that are reachable by the manipulator's end effect. So it's a collection of points, set of points that can be reached by the end effector of a manipulator. So you can get to that point in some fashion or the other. Then there is what is known as dexterous workspace. What is a dexterous workspace? Dexterous workspace derives from dexterity. What do we mean by dexterity? Dexterity is the ability to manipulate about a point. We can generate different orientations at a point. So dexterous workspace is a set of points where the manipulator's end effector can have multiple orientations. So it's a point in space where you can have multiple orientations. That means you have dexterity. Okay? So you can manipulate the workpiece any way you like. You have high dexterity. Okay. There is also what is known as a fully dexterous workspace. Fully dexterous workspace means you can generate any orientation you want. Okay, it's not limited to few orientations, but basically any orientation you want can be generated by the manipulator. So, fully dexterous workspace.
So the first definition is high dexterity.
High dexterity, that means you have multiple orientations. You can reach like this, anyway. But full dexterity is you can have any orientation you desire in 3D space. So this will be any arbitrary orientation in 3D space. You can fill that in. That means the set of points where the manipulator can generate any arbitrary orientation in 3D space. Okay, that means you can have fully dexterous. You can have any angle or any orientation you want in 3D space. There are two more important definitions, and then we can move to looking at different structures. Let's finish that, and then we'll go on to look at. One is accuracy, and the other one is precision. Okay. How do we define accuracy of a manipulator? Okay. So accuracy of a manipulator is how close can a manipulator's end effector reach a set point in 3D space. So if you define a point and ask the manipulator to go there, how close can it get to that point? Ideally, this should be 0, right? We want the error here to be 0 or as low as possible, right? Yeah. For a highly accurate manipulator, this will be 0 because it exactly reaches that point with no error. So how do we define precision? What is precision?
Minimum possible movement.
No, the thing is, most manipulators do a task repeatedly over and over and over. They're doing the same pick and place jobs. So in this case, this is how close a manipulator can go to a previously taught point. That means if it's doing that again and again and again repeatedly, so is there an error creeping up or it maintains a specific accuracy? So if the accuracy keeps on changing when it's doing that, then it is actually highly imprecise. But if it maintains a particular accuracy, then it's fine. How close the end effector can reach a previously taught point. So if it's trying to reach doing the same thing over and over, how close can it get to that point when it's repeatedly doing the same task? Okay. I think we have a little bit of time to look at manipulator, what do you call it, manipulator workspaces. So let's look at this. So when we look at a manipulator workspace, so let's say that I have a manipulator like this. Here I have θ1. This let's say is θ2. And this is θ3. This is A, R, R, R minus A. Okay, 3 degrees of freedom, R, R. The first joint is here. Okay. The other way to represent this is like this. So can we draw what will be the workspace of this manipulator? What will the workspace look like? So this is rotating like this, right? So it is rotating about this. These move up and down. Now, for most, for a general case, if you're not given any limitations, you normally tend to assume that a revolute joint will have 360 degrees of motion. That means it can go around itself. But that's generally not true, because every joint will have limitations. Even if it's a prismatic joint like this cannot extend till infinity, right? There is a certain maximum limit, d max, that it can go to. Similarly, even revolute joints have limitations. So typically a manipulator like this, when you look from the side, when you look at the workspace from the side, the workspace will be something like this. For this manipulator, it will be like this. When you consider the joint limitations, the workspace will be like this, because this joint is limited to how much it can move backwards. Okay. The top view is when theta 1 rotates. The top view will be like this. From the top, you will see the manipulator like this. You will only see these two links from the top, because this will be a point projection. So in this case, the top view will be. Okay. So if you call this link as A1, A2, A3, this will be only A2 and A2. When you look from the top, this is your top view of the workspace. This is the side view. Let me give you a very simple configuration, and you can tell me what the workspace will look like. Let's say.
So, Doctor, why the first link is not included in the top view?
Okay, so if you have a manipulator like this, right? These are the two links, and this is the third link, right?
Oh.
When I look from the top, this is going to be a point projection.
Yeah, okay.
You don't see this, right? Only when you look from the side, you will see this link. From our top view, this will be a point projection. Okay, let's tell me what the workspace for this looks like. You can assume the joint is fully revolute, so there are no joint limitations. So here's a manipulator. It is an RPP. So the first link is a revolute link. Then you have a prismatic joint P. Then you have another prismatic joint. Okay. This is theta 1. This is D2. This is D3. So this is a RPP manipulator. This is your revolute joint P. Okay. So what will be the workspace of this manipulator?
Only around the, only around the axis.
It will be round. Okay. What else?
Wide.
It's a cylindrical.
Cylinder.
Yes. So this will be up and down, and this will go forward and backward. So if you look from the side view will be just like this. The side view for this manipulator will be like this. Okay, because this is going to trace a circle. When this rotates, it will trace a circle, and it can go up and down like this. D2, and this will take it forward and backward. So when you look from the top view will be, depending upon the minimum and maximum displacement, this will be like this. Okay, this will be D3 max, and this point will be D3 minimum. Okay, so this manipulator is called, for obvious reasons, it's called a cylindrical manipulator. So a RPP manipulator, a 3DOF RPP manipulator is a cylindrical manipulator. All right. So all you have to do is imagine the motion of each of the joints. This will generate a circular motion because you're assuming this to be fully revolute. This will generate a motion. This will be the length of this. This will be due to motion of D2 up and down. This will be D3. Okay, and the motion along this is due to theta 1. Let's consider a different one, which is let's see. How about this? So this is a RRP.
Sphere.
Huh?
Spheres.
Sphere. Any other answer? What will be the workspace of this manipulator? Okay, so we're trying to plot the workspace. What will be the workspace of this manipulator? It'll be a sphere, right? So this will generate one motion, which is round, and this is going to turn it over. So this will draw a circle like this. This will generate a circle which is a disc like this. Okay? So the extent of the sphere will depend upon what is D3. So in this case, this is a RPP, is a spherical manipulator. So basically, this is going to generate a circle. When you rotate this joint like this, it will generate a circle. And